we were trying to understand it by mere cluster expansion is to write the canonical partition function. Okay, for just having a brief introduction because you were not all present in my previous class. So the canonical partition function for a interacting gas can be written as 1 by n factorial h to the power 3n and then integration of beta h taken h হচ্ছে Hamiltonian 3n p 3n q, and this translated to by putting the Hamiltonian to be p square by 2m and the potential to be a two-particle potential uij, I greater than j. If you put it over here, then you get z. এগুলো বোঝা যাবে না যাই was to really take into account this interacting potential uij, okay, and for that what we did was we assumed a mere potential which was, so the first part, this part within this is going to give us a factor of 1 by n factorial lambda to the power thrice n and e to the power minus beta summation of uij d to the power 3n r, okay? And we call this part as the configuration integral qn vt, and this was the canonical. So this was what we tried to configuration integral. And what Mayer did, Mayer and Arcel's formula, what Mayer did was to assume that this Mayer's function fij would be e to the power minus beta uij minus 1. Okay. Why this was so important? Again, because this is something which goes to infinity or because you have a temperature part, right? So for low temperature or for high value of uij, what is the nature of uij? We all know. What is the nature of the interaction potential between a pair of particles? Now, according to Lennard-Jones potential, you have seen that in your this is the nature of uij, okay? If you plot it versus rij, so you can see that this uij tends to infinity as rij tends to 0. There is a big force of repulsion when the atoms come very close to each other. So if you plot this, the advantage of using this Mayer's function was to if you plot the same thing over here, this was the equilibrium. So if you plot fij, okay, fij generator 0. So if you plot this, then it would be something like this and like this. So this is our fij. So the advantage of using Mayer's function was to take a finite value of fij, and then this is again the equilibrium distance where the atoms finally they tend to be found under equilibrium. Now, how do we translate this into a n particle graph? That also we have shown that if have this Q and Pt to be plotted for three particle. For example, if you want to plot this configuration integral, okay, in terms of the potential, in terms of the n particle graph, এসছে অলরেডি গতবারের পরীক্ষাতে, আমি জানি না এটা কি নতুন। এতে কালিনি ওকে, তাহলে আগে সেই ইয়েটা বের করা যাবে। Mean আচ্ছা, তোমরা কি কালকে প্র্যাকটিক্যাল করতে আসবে? হ্যাঁ, কালকে ছুটি কিসের? ও, তাহলে কবে তোমাদের প্র্যাকটিক্যাল থাকে? ও, আজকেই তাহলে হবে না? কটার সময় গো? এরপরে। বেশ, তাও what I was trying to say was you can always have a three particle graph. Should I repeat this or should I continue with my previous class? Ja পড়িয়েছিলাম তারপর থেকে পড়াই নাকি? কারণ কেউ কি ইন্টারেস্টেড এই আগের এই প্রশ্নটাতে? অনেকে জানে না, এটা পড়তেই চাও না। Cluster integral, do you need to learn cluster integral or do you want to know for the examination purpose? Is it necessary? পড়িয়ে দেবো, মানে আমি আগের দিন অনেকটা করেছিলাম, তারপর থেকে আমি তাহলে স্টার্ট করতাম আর কি, আগেরগুলো না পড়ে, কারণ আগের দিন ওই ছিল আর ও একদম লাস্ট টেস্ট ছিল ক্লাসে। তারপরে তুমি কিছু পড়েছো কি এটা? Not so much interested, but still syllabus টা তো শেষ করতে হবে, এবং কেউ যদি একজনও বুঝতে চায় তাহলে it is fine. যেটা বলছিলাম, so what I was trying was n particle graph কে কি করে লেখা হয়, মানে suppose you have n particle graph, okay, so for n is equal to 3, what can we do to write this configuration integral? Now I can write this as q1 3 Vp, because we are talking about n is equal to 3. So 1 q1 কেন বলছি না আমরা? Because now we can have a situation where all the three particles are independent of each other. There is no interaction. So I can write 1 2 3. এবারে যদি এটাকে আমরা টু পার্টিকেল ইন্টারঅ্যাকশন হিসেবে লিখতে চাই, it could be like 1 and 2 এর মধ্যে ইন্টারঅ্যাকশন আছে, 3 টা আলাদা আছে, অথবা 1 আর 3 এর মধ্যে ইন্টারঅ্যাকশন আছে, 2 টা আলাদা আছে, অথবা 2 আর 3 এর মধ্যে ইন্টারঅ্যাকশন আছে, 1 টা আলাদা আছে, অথবা 3 এর মধ্যে ইন্টারঅ্যাকশন। So this is how you draw. আরেকটা হতে পারে কি q3 3Vp, where you can have a pairwise, when all the three particles are involved in interaction. So this could be like this, or this could be like given like na eta ekhane hobe na, this would be here because two particle interaction, so this would be, so basically আমরা যেটা এখানে এরকম ইন্টারঅ্যাকশন এগুলোকে বলা হয় n পার্টিকেল গ্রাফ। গতবারের পরীক্ষাতে এরকম 3 পার্টিকেলের জন্য আঁকতে দিয়েছিল এবং এগুলো নতুন আমি আছি না, এটা অলরেডি পাথওয়েতে আছে, বাট অনেকগুলো বেশি পার্টিকেলের জন্য আছে। এবং এখান থেকে আমরা বলতে পারি যে if ml be the number of L cluster, so these are called one cluster. This first one is called one cluster, second one is called two cluster. Why? Because each particle constitute a cluster for the first graph. Here two particles may constitute a single cluster and one particle for another cluster. Here you have three particles, so this is a three cluster. So in this fashion you can go on up to L cluster. Suppose you have L cluster system because you have so many particles and we want to, this is nothing but the part of the canonical partition function, the configuration integral, the integral which contains the coding. Okay, if you have such L clusters and if you have ml number of such sub clusters or ml number of configurations, okay, so if there are m1 one cluster where it is 3, you can see 1 2 3, okay, m2 two cluster, so there is a rule which I have proved in our previous class that LML must be equal to the total number of particles for which we are drawing such n particle graph. So this is the rule of law where L runs from 1 to n. Okay. So that gives you LML. So this is what we did in our last class. Let us try to find the exact expression with this particular knowledge of L clusters and ml number of configuration. Let us try to find out the expression for the configuration integral, because this part t square by 2m dqn আর যেটা রয়ে গেল সেটা হচ্ছে e to the power minus beta uij. This part is actually our qn vt. So we want to write this qn vt is basically equal to summation over all configuration and sum of all possible mls. Okay. So this n particle graph having different mls. Mls are the number of the different configuration, because your partition function, what does it give? It gives you the number of possible microstates, okay, or number of possible ways of arranging the number of particles. So here also we can say that sum of the L particle graphs, summation over ml, summation over all possible configuration, that is going to give us this configuration integral. So we would like to really find an expression. So I can write, what is this SML then? Now I can write this in terms of the above graphs as the number of the one particle cluster plus number of the two particle cluster. So this was 1, and number of the three particle clusters and so on. What does this summation of or sum of all possible graphs is the, so there are one particle cluster for a 3-particle system, because this is one cluster, this is another, this is another. There are 3 different configurations. This is one configuration, you have a 2-particle cluster, this is another configuration, and here 3 particles cluster, 1, 2, 3, 4. So there are 4 different types of. So if you sum them up, then you get SML. For each ML, you add them up and you get the configuration integral. Okay. So how do I really write an expression, a precise expression for SML? Now each term of this curly bracket for different configurations are to be added over L clusters, and if the bracket are expanded for multinomial expansion, it's not a binomial. For 2 it would be binomial, but if it is more than 2, then it would be a multinomial expansion. Okay, so for each particular bracket, if you expand them, then you get multinomial configurations, and the summation would extend from 1 to n, so p running from 1 to n. And there is another thing which needs to be remembered, and that is defined as the Mayer's cluster integral. That is Mayer's, this is something integral, and this is defined as BL. Okay, and this BL is 1 by L factorial lambda to the power 3L minus 1 into V, and then multiplied by sum of all possible L clusters. This is something really important. This is a kind of axiom which Mayer gives. He said, why this is divided by L factorial? Because there could be L such configurations, and each configuration is equivalent. So we divide this by L factorial. What was lambda? It was the de Broglie mean free path, h by root over of twice pi m kt. So lambda cube, lambda to the power minus 3, and volume. So that makes it dimensionless, and lambda to the power 3n or 3l. Why is it coming? Because here it was there. See, it was 1 by n factorial lambda to the power thrice n. So for L cluster it would be 1 by L factorial lambda to the power thrice L, and then I multiply a lambda to the power minus 3 into V to make it a dimensionless parameter. So the volume is there, and there is a lambda to the power minus 3. There must be a volume, because previously we calculated certain of the, no, we didn't calculate. I will calculate today and I will show you. And then it is multiplied with sum of all possible L clusters. So let us try to check on how would it look like. Let's say I shouldn't have erased the pictures. In Chobiko Thakley it would have helped you a lot. But let us try to calculate certain B's. This B. So what is B1? Let's say if I, for your, first of all let us try to calculate B1. And in terms of picture also I want to, this is the single particle cluster. So B1 is 1 by V single particle, one particle cluster. That's why, because this was for L particle cluster. And what is that? If you have a single particle cluster, so that is equal to 1 by V, because you see, if B1, then this is 1 factorial lambda to the power 3, 1 minus 1 is 0, so there is only 1 by V, and then there would be a PQ R1, so that gives V over V. So our B1 is always 1. Okay. This is the question which was given in our last year question papers. Calculate Then if I talk about B2, so B2, what would be B2? Now if you draw in terms of the picture, then it would be 1 by twice lambda cube V, and this is the picture, okay, two particle graph. And if you really put it in the expression over here, so it would be 1 by 2 factorial lambda cube V and F12 B cube R1 B cube R2. Where F12 is the, because we are talking about only two particles, so here Mayer's function would be either I is 1 and j is 2 or vice versa. So if that be the case, then you can take out one of the coordinate away, and then you can write it in terms of the relative coordinate. So if you take one of the coordinate outside the integral, it's going to give you the, suppose you have only two particles and you sit on one of the particle and then see the movement of the other particle. So you can always fix the R1 or taking R1 outside the integral. So it would constitute the volume about R1. So if it is about R1, then you can always pull out R1 from the integral, and then you can take it as B by 2 factorial, and then you can write F12 B cube R12. Since you are sitting on the particle 1, so your position vector of the particle 2 will be with respect to 1. That's why I call it R12. Now our R2 will be R12, and I pull out from the integral dq R1. So that gives us a volume. So then it can be written as 1 by twice lambda cube F12 dq R12. Okay. In the same fashion, one can calculate B3, but as you go on, the situation would become more and more complicated. For example, in this case, it would be 1 by 6 lambda to the power 6V, and the particle graph would look like 1, 2, that same picture. Okay, 1, 2, 3 plus 1, 3, 2, and so on. Okay, so B3 can be written again in terms of 1 by 3 factorial lambda cube V, and then you have F12, F23, F12, F13, F13, F23, and F12, F13, F23, and D cube R1, D cube R2, D cube R3. And again you can see or check on that these terms are more or less equivalent. Why? Because they are actually representing the Mayer's function for a pair of particles, and this is something which is actually taking into account the interaction of all three. Okay, so this is F12 and F13. This picture corresponds for this F12 into F13. This picture, oh sorry, you can go here. So this is this, and okay, and F1 to F13, F1 to F13, F1 to 1, sorry, F1 to 13 is this, F1 to 3, this is this, and F13, F23, this is this, and for that, for this, if you want to draw a picture, then 1, 2, 3. So this corresponds to this picture corresponds to this lambda to the power 6. Okay. কারণ এখানে হচ্ছে 3 into so this is going to give us, and if you go on solving this is going to give us 1 by 3 factorial lambda to the power 6, and this is going to give us 3b f1 to f1 3 d cube r1 to d cube r1 3 plus b into f1 to f1 3 f2 3 d cube r1 to d cube r1. So this b and this cancels out, and you are left with something like 2b2 square plus 1 by 3 factorial lambda to the power 6, and f1 2 f1 3 f2 3 d cube r1 2 d cube r1 3. So this is how you can go on calculating this value of the Mayer's cluster integral. What we want to do in our today's class is to really calculate the value of the partition function for a real gas or an interacting gas. So we need to calculate the sum of the all possible L cluster system. So how do we do that part, the configuration integral part? So Qn Vp was defined as summation over different ml configuration, and sum was taken over all possible graphs. That means this is the sum of all possible L cluster is this. This is S of ml, which we want to evaluate by using this graph. Now, if you really want to write this SML, you need to first of all check out how many configurations are there. Suppose you have n particles, so there are n factorial configurations. So it would be n factorial, and this n factorial is always over counted. Why? Because for each particular cluster you have again different configuration. So you divide it by, if there are one particle cluster, so it would be 1 factorial to the power m1, 2 factorial to the power m2, and so on. So you can write this as n factorial by pi of, pi means product of L factorial to the power ml. But this is not the whole story. There is certain problem, because for each particular ml, again you have a different possible combination. See here, although the particle number is 3, but if you have the 3 cluster system to contain more than 3 different configurations, it is 1 this, 2, 3, 4. So you can have 4 possible configurations even for a simple 3 particle system, if they have 3 particles to be simultaneously having interaction. Okay? So this is something which can give you wrong value. So what you do is you multiply this with L by this with again the product of the value of an L cluster to the power ml. And if you make everything finally boil down to a simple thing, then you can write this is the quantity which is what we want to have. This is the one. So what we do is we write this QML to be like n factorial, this n factorial, lambda to the power thrice n, and then summation over different mLs, okay, and pi of L dl V by lambda cube whole to the power ml by 1 by ml factorial now the question is যে হচ্ছে কোথা থেকে এই টার্মটা এলো where from sum of all possible states of a cluster, that is what I claimed as SML, so that would be equal to BL into L factorial or so L factorial because we are dealing with n number of particles, that is becoming n factorial lambda to the power thrice n, okay, and then into V by lambda cube current lambda to the power and whole to the power ml. ml cannot because there are ml different configurations, and those ml configurations, if you interchange them, then they are not going to give you a new configuration. Okay. So that's why you divide it by ml factorial, you take a power with respect to ml of this quantity, and that is what is given by QNVP. So if we return back to the canonical partition function, now I can write this again, the canonical partition function here, ZNVP, okay, ZNVP. The first part was 1 by n factorial h to the power 3n and lambda to the power, okay, h to the power 3n, lambda to the power 3n, because after integrating the momentum part, it gives us root over of twice pi mkt whole to the power n, okay, twice n. So that is giving us, and if you multiply this with again, so this part cancels out, and what you are left with is this quantity which corresponds to the n particle graph of L clusters. Okay, where we have used L into, see, if this is lambda to the power ml, here we have used lambda to the power ml 3 times lml to be equal to thrice n. এটা কোথা থেকে বেরোলো, কারণ এই নিচে আমি এক্সপ্রেশনটা বুঝে দিলাম, ওখানে কিন্তু lambda to the power actually lambda to the power 3 L cube ছিল তো, so that is going to give you L ml, কারণ to the power বলতে পারো যে এটা কোথা থেকে এলো, এটা তো to the power ml হলো, ওই L ml সামেশনটাই কিন্তু lambda to the power thrice n দিল আর কি এখানে, so that part actually cancels out and you are finally having this as the canonical partition function of interacting system. But if you want to take the grand canonical partition function where actually your number of partition if you want to even vary them, because the number of particles also doesn't remain constant, and if they are not remaining constant, what do you alter actually? You you write the grand canonical partition function as a function of f vt, where or mu vt, okay, where f is the fugacity. You remember fugacity, which was equal to e to the power mu by kt. Okay. So if you want to write the grand canonical partition function, what do? Now we multiply the canonical partition function with f to the power n. So this is basically equal to f to the power n z n dt. So if we multiply this to be f to the power n, okay, n means the number of the particles, so f to the power capital N, because we are dealing with n particle graph. So if I now write this to be equal to f to the power n, and zn dt was like pi to the pi l dl v by lambda cube to the power ml divided by ml factorial. So this can be written, f to the power n can be written as e to the power mu by kt, and what is n? Summation of l ml. Karan equal to the power ml acid. So we take this to be again pi of e to the power mu l by kt whole to the power ml. So I can write this to be equal to f to the power l. Okay. So I can just include this pi to the power f to the power l dl v by lambda cube ml, and this whole thing divided by ml factorial. But then এই পাইটাকে যদি আবার এর মধ্যে ঢুকিয়ে নি, then I can, this is basically a product of this, so I can always write this to be summation over ml. Okay, then I can write this pi of, what is this quantity? X to the power ml by ml factorial. Now this is basically পরে আমাদের practical ক্লাসটা আছে, so I would wind it up as fast as possible, because so I can write q f vt. q f vt is the grand canonical partition function, and that can be written as summation pi. So this would be pi of summation of dl v by lambda cube f to the power l to the power ml by ml factorial, which is nothing but exponential of dl v by lambda cube f to the power l. This is the expression, and dl v by l running from 1 to infinity. So you can have all possible interaction with the number varying. Now if I ask what is the equation of state in the case of in the limit of v tending to infinity, one can write 1 by v. From here you can write ln of q f vt equal to 1 by lambda cube summation of dl. This is one of the Mayer's equation. এটা এখান থেকে সহজে পাওয়া যাবে। আরেকটা ইকুয়েশন হচ্ছে limit v tending to infinity for infinite volume, one can write e by kt to be equal to 1 by lambda cube summation of dl EL f to the power L. This is another equation. So these are the two different equations from which simply providing the value of EL we can arrive at the van der Waals equation of spin. Okay. So this more or less completes our Mayer-Ursel's cluster integral, and please go through the book of Patria and you would understand that, because this class was not so delightful.